Okay, the next thing is applications of this resonance. There are various applications of series LCR circuit under resonance condition. One of them is tuning circuits and radio sets. Tuning circuits in radio sets. So have you used these radio sets ever? Radio sets with not auto-tune radio sets which have a knob to tune the stations. Fatma, Jubaina, have you used these radio sets in which there is a knob to adjust the station? Yes, exactly. In car. In car, you have these types of radio sets where you can adjust the knob and can select the stations, right? Okay. So those tuning circuits are basically the LCR circuit, and just by shifting the knob, you are shifting the resonance frequency. Say if a particular radio station is at a frequency of 95 megahertz. There's a radio station which is at some 95 megahertz frequency. That means if you want to select that 95 megahertz of frequency, that means you are rotating the knob, you are changing the resonance frequency of the circuit, and you're trying to make the resonance frequency of your circuit equal to 95 megahertz. See, this is inductor, this is capacitor, this is resistor. This is your radio set, a typical radio set. And this is the input. All available stations are here. Let's say from 90 megahertz to 110 megahertz, all radio stations are available. But that radio set pick one station at a time. It does not pick all stations simultaneously. It pick one station at a time. Picking one station at a time means it is picking one frequency at a time. The radio set is picking one frequency at a time. From 90 megahertz to 110 megahertz, it is picking one frequency at a time. So to pick that frequency, we use the concept of resonance. The resonance frequency of the circuit is 1 by 2 pi root over LC. In radio set, capacitor is variable. When we rotate the knob, we are basically changing the value of capacitance. L is fixed, but we are changing C. We keep on changing the value of C until the resonance frequency becomes equal to 90 megahertz. When resonance frequency of the circuit is equal to 90 megahertz, this circuit select that particular station corresponding to 90 megahertz frequency, and you start getting that station. So this is how we use series LCR circuit to tune radio sets. Say you don't want to select station corresponding to 90 megahertz. You want to select a station which is corresponding to 110 megahertz. So what you will do? You will again rotate the knob. By rotating knob, you are changing the value of capacitance until the resonance frequency is equal to 110 megahertz. Once the resonance frequency is equal to 110 megahertz, the station corresponding to 110 megahertz gets selected, otherwise others are rejected. This is how we tune radio sets. So I'm just writing a small note. Series LCR circuit. The second application of this series LCR circuit is in metal detectors. The metal detectors which are available at airports, metro stations, those metal detectors are again the series LCR circuit. So in metal detectors, there is a wooden chamber in which you enter. So that wooden chamber is basically a hidden inductor. That wooden chamber is an inductor basically, which is connected to a capacitor, which is connected to a resistor and to an AC supply. This resistor is basically an alarm. This alarm is adjusted in a way that if your circuit is in resonance, then this alarm will remain off. This alarm will remain off until your circuit is in resonance. The resonance frequency is 2 pi 1 by root over LC. Until your circuit is in resonance, this alarm remains switched off. This alarm is not on. But if you enter, so let's assume that the frequency here, the external frequency is 100 Hertz. And I have adjusted the value of L and C so that the resonance frequency is in 100 Hertz. I'm using a particular value of L, a particular value of C so that the resonance frequency is 100 Hertz. Means your system is in resonance, this alarm will remain off. But once you enter in this chamber with some metal, metal will change the self-inductance. Due to change in self-inductance, this resonance frequency will change. When resonance frequency change, your current drop from maximum to a lesser value. Because at resonance, your current is maximum. If resonance disturb, then your current falls from maximum value to a lesser value. This alarm detect this change in value of current. So as your current falls from maximum to a lesser value, this alarm gets activated. So the alarm in metal detector basically detect the change in resonance frequency. I'm repeating it again. Metal detector is an LCR circuit. The wooden chamber in which we enter is basically an inductor, hidden inductor. This circuit is in resonance. Resonance frequency 1 by 2 pi root over LC. When the circuit is in resonance, your current is maximum. This is an alarm. This alarm is adjusted in a way that if the circuit is in resonance, current is maximum. This will remain off. But when you enter in this chamber with some metal, metal will change the self-inductance. Due to change in self-inductance, this resonance frequency will change. This resonance frequency, so once the man enter in this metal chamber with in this wooden chamber with some metal, the resonance frequency gets changed. Once the frequency change, your current is no more maximum. It will attain some lesser value. This alarm will detect that your current is not maximum now. It will get activated. This is how a metal detector works. It's again the same LCR circuit. The next quantity is known as quality factor. Next quantity is basically quality factor. Quality factor basically decides the selectivity of the circuit. I'm explaining what is selectivity. Sharpness or selectivity of resonance. There are various definitions of quality factor. So sharpness or selectivity means if I draw two resonance curves, so you're basically measuring the sharpness of the peak. So these are two curves. This is one and this is another. This is curve 1. This is curve 2. So this peak, say this curve is less sharp than curve 2. This sharpness of the curve is decided by this quantity which is known as quality factor. Greater the value of quality factor, greater would be the selectivity. So if I say the quality factor is Q2, if I say here the quality factor is Q1, so Q2, we represent quality factor by Q. This is Q2 is greater than Q. This is quality factor. So now you understand what is the sharpness. Sharpness through the curve, this peak value, that's it. This is sharper than this one. So this have a higher value of quality factor than this. Now see how this sharpness will affect the working of LCR circuit. Like practically what is quality factor? How quality factor affect the quality of a tuning circuit. Say you have two radio sets. You have two radio set. One radio set is having curve of this type. Another radio set have curve of this type. So the radio set having this type of curve is very selective. It's selective means its quality is very good. It will select up one station at a time. There is no noise in this type of radio set. It will select one radio station at a time. But if you are using a radio set having this type of curve, then here the quality is bad. This can select two or more radio stations simultaneously. So if in your radio set, two or more stations starts simultaneously, then there is noise. You won't understand what is happening. So this quality factor basically decides the selectivity of the circuit. Greater the value of quality factor, greater would be the selectivity. Greater selectivity means it will select one station or one channel at a time. It will select one channel at a time. But this can select simultaneously many channels. So it's basically bad quality. You won't understand what's happening. You just observe noise. So this is quality factor. Okay. After this, there is one more definition of quality factor that can be used. It's omega. That is. And this is the resonance curve. There is one more definition of quality factor. This is your current. This is the maximum value of current. So this is I naught max. And this maximum value is at a frequency which is known as omega naught. It's resonance frequency. Now, every radio set has some limits. It works well within a defined frequency limit. A defined frequency limit means the radio set that you may be using in your car and the radio sets that traffic police use. Both are radio sets. But using your radio set of car, can you select the frequencies of the traffic police? Can you select those frequencies at which that traffic police communicate? Why not? Well, both are radio sets. Both are selecting frequencies. But using the radio set that you use in car, you cannot select the frequencies which basically the police is using. There are many reasons. One of them is every radio set have a frequency range in which it works effectively. It is designed in that particular range to work in that particular frequency range. Beyond that frequency range, your radio set does not work effectively. You cannot use your radio set beyond that frequency range, the one for which it is designed. So for this particular radio set, let's say this is the frequency range, omega 1 to omega 2. This is the frequency range in which your radio set works effectively. So this frequency range is known as bandwidth. The definition of bandwidth is very simple. It's the frequency range for which your radio set is defined. That is bandwidth. That's it. And this is true not just for your radio set. This is even true for mobile phones. Mobile phones are designed for a particular frequency range. So that's why if you move from, say, India to UAE or UAE to European countries, mobile set have certain issues. It's designed for a particular frequency range, and that particular frequency range is known as bandwidth. So what is bandwidth? Bandwidth is frequency range in which tuning circuit works effectively. That frequency range is known as bandwidth. So here bandwidth is twice of delta omega. That is the bandwidth. There's one more thing that you should remember for questions. See, corresponding to omega naught, your current is I naught max. But corresponding to this omega 1 and omega 2 frequencies, your current is I naught max divided by root 2. I cannot prove why at frequency omega 1 your current is I naught max by root 2. It's not a part of your syllabus. But we will use this as a fact in few derivations and numericals. So this thing you should remember, that corresponding to frequency omega naught, your current is maximum. But if your frequency is not omega naught, it's omega 1 or omega 2, which is basically bandwidth, your current is 1 by root 2 times the maximum value. Similarly, you should remember that at resonance, your power is maximum. This is average power, which is maximum. But over these frequencies, omega 1 and omega 2, your power is just half of maximum power, P max by 2. In numericals, we will use both these facts. That at omega naught, your current is maximum. At omega 1 and omega 2 frequency, your current is I naught max by root 2. At omega naught, this is power, average power. Your power is maximum, but at omega 1 and omega 2 frequencies, your power is just half of maximum power. The next definition of quality factor is quality factor is ratio of resonance frequency and bandwidth. So the ratio of resonance frequency and bandwidth is known as quality factor. We represent it by Q. Resonance frequency is omega naught. Bandwidth is twice of delta omega. This is quality factor. There's one more expression of quality factor, which is basically 1 by R root over L by C. Now, there is one small calculation to derive this expression from this definition. So we have to derive this particular expression with this definition of quality factor, that how resonance frequency by bandwidth is actually equal to 1 by R root over L by C. Okay, we start this derivation using the expression of current. At resonance frequency, the expression of current is, your current is maximum, I naught max. And this is basically E naught divided by R. So this is at resonance frequency omega naught. So if you look at this curve, at omega naught, I take this thing, current is maximum. Now I'm taking frequency omega 2. At frequency omega 2. Now, can you tell me what, sorry, not here. At frequency omega 2. Okay, just tell me, how much is current at frequency omega 2? Is it maximum? At frequency omega 2, how much is current? Is it maximum? It's not maximum, it's I naught max. See, at omega 2, your current is not maximum, it's maximum value divided by root 2. So it's basically I naught max divided by root 2, which is equal to E naught divided by Z. And Z you can write, this is E naught divided, because omega 2 is not resonance frequency. Z is not minimum. Z is XL minus XC square plus R square. That's equation number 1 and this is equation number 2. Is it clear? Equation 1 and 2? It's okay. So the next you can do is you can divide 1 and 2. Just divide equation number 1 and 2. When you divide 1 and 2, you will get this is I naught max divided by I naught max by root 2. It's E naught by R divided by E naught by root over XL minus XC square plus R square. Let's cancel out. Let's get cancelled out. So it's root 2 and this is XL minus XC square plus R square divided by R. You can multiply with this R to the left hand side and we are left with root 2R is root over XL minus XC square plus R square. Now you can square both the sides. You can take square both the sides. When you take square on both the sides, you will get 2R square is XL minus XC square plus R square. Take this R square to the left hand side. It's 2R square minus R square is XL minus XC square. So you have R square, which is XL minus XC square. Next, you can take roots on both the sides. Taking square root, you are left with R is XL minus XC. That is equation number 3. So this is R, which is basically XL minus XC. Next, what we can do is you can substitute your XL as omega L, omega 2L. Your XC is 1 by omega 2C. In the next step, you can write your omega 2 as C. From the figure, it's clear that omega 2 is omega naught plus delta omega. You're adding delta omega to omega naught. So your omega 2 is omega naught plus delta omega. Omega 2 is omega naught plus delta omega. So when I substitute all values here, your R is omega naught plus delta omega into L minus 1 by omega naught plus delta omega multiplied by C. This is your R. Next, we can do few simplifications. The first simplification is take omega naught common. If I take omega naught as common, then I'm left with 1 plus delta omega by omega naught into L minus 1 by. Again, from denominator, you can take omega naught as common. If omega naught is common, you are left with 1 plus delta omega by omega naught to the power C. You can take this 1 plus delta omega by omega naught in numerator. So you are left with it's omega naught L. This is 1 plus delta omega by omega naught. And the next is you have 1 by omega naught C. You have 1 plus delta omega by omega naught to the power minus 1. Delta omega by omega naught to the power minus 1. Next, what you can do is omega naught is you can substitute the value of omega naught. So, not omega naught. You know that omega naught is 1 by root over LC. So, you can take square. Omega naught square is 1 by LC. And you can say that 1 by C is omega naught square. I call this as equation 3 or it's 4? It should be 4. I call this as equation number 4. And this is equation number 5. I substitute 5 in 4. When I substitute 5 in 4, you will get R is omega naught L 1 plus delta omega by omega naught minus 1 by omega naught. This is 1 by C, which is omega naught square. It's omega naught square, which is 1 plus delta omega by omega naught to the power minus 1. So this omega naught square will cancel this thing. So your R is, it's omega naught L. This is 1 plus delta omega by omega naught minus omega naught L. It's 1 plus delta omega by omega naught. So have you done binomial expansion? Have you used binomial expansion ever? You all have maths. You know binomial expansion? Yes, you all know. So in binomial expansion, I can write 1 plus x to the power n as 1 plus nx if x is small, less than 1. If x is less than 1, then you can write 1 plus x to the power n as 1 plus nx. Here this is n, 1. This is your x. See, this is delta omega by omega naught. It's less than 1 because delta omega is small. Omega naught is large angular frequency. This is less than 1. And this is n. So if I expand this using binomial expansion, I'm left with omega naught L 1 plus delta omega by omega naught minus omega naught L. It's 1 minus delta omega by omega naught. So you can take omega naught L as common. This is left with delta omega by omega naught minus 1 plus delta omega by omega. So this 1 will cancel this 1. Your R is omega naught L. It's twice of delta omega by omega naught. So from here, you can write that R by omega naught L is twice of delta omega by omega. So if I take reciprocal of this equation, so this will be omega naught L by R is omega naught by twice of delta. So can you identify quality factor in this equation? Is there any term which match with quality factor? Yes, this is the quality factor, right? This is the definition of quality factor that we have written. It's omega naught by twice of delta omega. So it's a lengthy calculation which gives quality factor equal to omega naught L by R. From this omega naught L by R, you can calculate that second expression. So your quality factor is omega naught L by R. Instead of omega naught, you can write it's 1 by root over LC into L by R. So see, this root L will cancel this L and you are left with 1 by R root over L root over C. Because this is root L, this is L. It gets cancelled out. There is one root L in the numerator and root C here. So that's the derivation. It's a 5-marker question if it came. It's a part of syllabus, but for the last 5 years or maybe in 10 years, I haven't seen this derivation in question paper, but it is a part of syllabus. This is given in NCERT. A series LCR circuit So when asking the source frequency for which current and amplitude is maximum, that means he's asking about the resonance frequency. This is the formula. 1 by 2 pi root over LC. Then obtain the maximum value of current. The maximum value is this. I naught max is E naught by R. In the same way, the frequency for which power is maximum is again resonance frequency. The part 1 and 2 is asking about the same frequency. Only the language is different. And obtain the maximum power is this. P max is E RMS into I RMS. And one more thing, this is the RMS value. In the first part, asking about resonance frequency, which is 1 by 2 pi, it's root over LC. So it's 1 by 2 pi root over L, where L is this 0.12 Henry, multiplied by capacitance. Capacitance is 480 nanofarad. When you solve it, it comes out to be around 663 Hertz. Now, if you want the peak value of current I naught max, that is basically E naught divided by R. You can write this E naught in terms of E RMS. E naught is E RMS multiplied by root 2, right, into R. So it is given that E RMS is this 230 and your R is 23 ohm. So it's 230 by 23 into root 2. It gets cancelled out. So this is I naught max, which is basically 10 root 2 ampere. So that's the first part of the question. The second part, he's asking about the frequency for which average power is maximum. It's the same frequency, the same resonance frequency. So the answer of first part is same exactly. It's 1 by 2 pi root over LC. This is same, 663 Hertz. In the second part, you're supposed to calculate the maximum power. This is maximum power. It's E RMS into I RMS. You have I naught. So this is E RMS. And this is maximum, by the way. It's resonance, so current is maximum. So this is I naught max by root 2. So how much is E RMS? E RMS is 230. How much is I naught max? That's 10 root 2 divided by root 2. They gets cancelled out. So your maximum power is 2300 watt. And the last part, third, quality factor. See, quality factor is just 1 by R root over L by C. You can substitute all values. Is 1 by R is 1 by 23. It's root over L, 0.12 divided by C, which is 480 nanofarad. When you solve this quality factor comes out to be 21.7. Choke coil. So choke coil is basically an ideal inductor which can be used to reduce current in the circuit. It is an inductor which can be used to reduce current in the circuit without much loss of energy. See, to reduce current, you can even use resistor, but resistor has certain limitations. To reduce current in the circuit, you can also use resistor, but resistor have certain limitations. Resistor reduce current, but a part of electrical energy is wasted as heat because resistor gets heated up. A part of your electrical energy will get dissipated as heat. But instead of resistor, if you use choke coil, then you can control current in the circuit. You can decrease current in the circuit without any actual loss of power. There's no power dissipation. All your power dissipation is minimum. See, you have this inductor. You connected this inductor to an AC supply. Self-inductance is XL. So the current is E by XL. So greater the XL, smaller will be the current. So you can reduce current in the circuit. But if you try to calculate the average power, that's ERMS, IRMS, cos phase difference is 90 degree. So your average power comes out to be 0. Average power dissipation is 0. So if you have a circuit having only inductor, then the average power dissipated is always 0. That's basically a choke coil. So choosing choke coil, you can control your current, but without any loss of energy in the form of heat. So that's why choke coil is better than resistor. After this choke coil, the next definition is of wattless component of current. Wattless component of current. We know that wattless current means power dissipation is 0. Wattless, yes, Jabana. Power, average power dissipation is 0. Average power dissipated is 0. That's wattless current. See, what is wattless component of current? Basically, if let's say this is your current, this is your EMF, the phase difference between them is phi. This is IRMS. This is ERMS. This is the cost component of ERMS. It's ERMS cos phi. And this is the vertical component of ERMS. ERMS sin phi. Phase difference between this ERMS cos phi and this ERMS sin phi is 90. This is the phase difference between, this ERMS sin phi and this IRMS. Say the phase difference between ERMS and IRMS is phi. So I take component of ERMS. A component along IRMS is ERMS cos phi. The component which is perpendicular to IRMS is ERMS sin phi. So you can say that this ERMS sin phi is perpendicular to IRMS. So ERMS sin phi is perpendicular to IRMS. So Froza, what is the phase difference between ERMS sin phi and IRMS? Just by look at this diagram. The phase difference is pi by 2. They are perpendicular to each other. Phase difference between this quantity and this quantity is 90 degrees. They are perpendicular. So if you want to calculate average power due to this ERMS sin phi, then this average power comes out to be its ERMS sin phi multiplied by IRMS multiplied by 90 degree. Sorry, cos 90. This is how we calculate average power ERMS, IRMS, cos 90. So this P average is equal to 0. Since average power dissipation due to this ERMS sin phi is 0, so we call this ERMS sin phi, which is perpendicular to IRMS, as waterless component of current. At waterless component of current. After waterless component of current, there is equation of instantaneous power. Average power, you know that average power is ERMS, IRMS, cos phi. This is instantaneous power. Instantaneous power is the product of instantaneous EMF and instantaneous current. It is the product of instantaneous EMF and instantaneous current. So instantaneous power is instantaneous EMF, which is E naught sine omega t. Instantaneous current is I naught sine omega t plus phi. This is your instantaneous power simply. The product of instantaneous current and instantaneous EMF. There's one more definition, that is average power. Average power is basically the ratio of work done in one cycle, time t divided by t. That's your average power. So I'm giving you some hint of numericals. Maybe in some numerical, he can ask you to derive the formula of average power. To derive the formula of average power, you can use this thing. First, you can use instantaneous power, which is dW over dt. Your work done comes out to be P dt. For the whole cycle, you can calculate your work done as, there's very small chances to get this calculation, but this is your work done in time t. Average power is just 0 to t P dt divided by T. That's it. P, you know, P is this equation. P is instantaneous power. So average power is 0 to T. I'm integrating this instantaneous power E naught, I naught, sine omega T, sine omega T plus phi dt divided by T. You know how to integrate it. In the starting calculations of AC, in the calculation of IRMS and I average, we have discussed how to integrate this expression. So this is how we calculate average power. Then there is one last topic, which is basically transformer, last device which is transformer. The last device is transformer. So in day-to-day life, we call transformer as stabilizer. Transformer is basically a stabilizer. What stabilizer do? So what stabilizers basically do, stabilizers can increase the voltage or they can decrease the voltage. They can do both the things. They can increase the voltage or they can decrease the voltage. So basically, when in India we use stabilizers with AC, basically try to maintain a constant voltage. If voltage decreases, let's say I fix the stabilizer at 200 volt. If the value of AC voltage is greater than 200 volt, then it will decrease it to 200 volt. That's known as step down in technically in the language of transformer. If it decrease from 200 volt, then this stabilizer can increase it up to 200 volt. It can maintain a a fixed supply of 200 volt. So it can decrease voltage or it can increase voltage. Even you have transformers in your locality. I don't know you have there or not. In India, we have even have transformers in locality, big transformers in locality, which are the motive of those transformers is just to step down the voltage, because the voltage that you are getting from power station is very high. It's 20,000 volt, 50,000 volt. But the voltage that you use at your home is a comparative low voltage. It's 220 volt. So you need a device which can convert the voltage of 5,000 volt to the usable 220 volt. That is stabilizer, or in principle transformer. So transformer, it is a device which can convert low voltage to high voltage by decreasing current. So when it decrease voltage, it decrease current, or vice versa. Or it can convert high voltage to low voltage, or vice versa. So that's basically a transformer. It converts low voltage to high voltage by decreasing current, or it can convert high voltage to low voltage by uh, increasing current. So when it increase voltage, it decrease current. When it decrease voltage, it increase current. That's transformer. So the principle of transformer is it's basically works on the principle of mutual induction. Yeah, so what is mutual induction? When you change current in one circuit and it gets induced in another, or you change voltage in one circuit and it gets induced in another, that is mutual induction. So this principle It works on the principle of mutual induction. That's the principle of transformer. Next construction. A typical transformer have two parts. Basically, it have a core, this type of core. This is the core of transformer. And in this core, this is core basically of soft iron. So this is soft iron core. At one end of the core, you have some turns of wire, and this is connected to an AC supply. Basically, this is the end of stabilizer which is connected to the supply, to the power supply. And there is another end which is connected to the load. Load means like if I'm connecting my stabilizer to an AC, then that AC is load and this is your AC supply. So this is your AC supply. This is primary. And this is secondary. That is primary and this is secondary and this is load. So this is basically a typical stabilizer or typical transformer. This is primary which is connected to the AC supply and this is secondary which is connected to the load. There is no direct connection between primary and secondary. From primary to secondary, the voltage, you can say that voltage travel from primary to secondary using mutual induction. In primary, you have AC. AC is variable. When voltage change in primary, then it gets induced in secondary. So it's basically working on the principle of mutual induction. The voltage at the primary is Vp. The voltage at the secondary side is Vs. So Vp is voltage at primary. And Vs is voltage at secondary. Is it? Then you have number of turns, NP. See, this is coil which is wound over the soft iron core. So the number of turns at the end of primary is NP. And here the number of turns is Ns. NP, number of turns in primary. And Ns are number of turns in secondary. Ns are simply the number of turns in secondary. Then there is phi. With each turn of primary, the flux linked is phi. So phi here is flux linked with each turn of primary. With each turn of primary, the flux which is linked here is phi. So you can say that, see, this flux which is linked with the primary is not a constant flux, it's a variable flux. This is connected with an AC source. So phi is variable. So when phi change, an EMF is induced in the primary. So you can say that voltage across primary Vp is, if you can remember Faraday's law of electromagnetic induction, minus Np d phi over dt. This is the voltage across the primary, Np d phi over dt. This is first equation. Yes, Giovanna, is it clear? This equation number one? Okay, then you can, now the primary and secondary are inductively coupled. Inductively coupled means flux which is linked with each turn of primary is also linked with each turn of secondary. Means if flux phi is linked with each turn of primary, the same flux is linked with each turn of secondary. Flux means magnetic field. When magnetic field travels from primary to secondary, it remains same. Although it's an approximation, because you know that magnetic field strength decreases with separation. Here magnetic field is strong, here it should be weak. But we are taking this approximation that magnetic field at primary and secondary are more or less same. And that approximation is known as they are coupled. Assuming no flux leakage, each turn same flux is linked with each turn of secondary. So Vs is minus of Ns d phi over dt. That is equation number 2. So that is Vs. You can take the ratios like Vs by Vp is minus of Ns d phi over dt. It's minus of Np d phi over dt. It gets cancelled out. It gets cancelled out. So Vs over Vp comes out to be Ns over N. So that is the relation between the voltage across secondary and voltage across primary. See here, the voltage across secondary is proportional to number of turns in secondary. Voltage across primary is proportional to number of turns in primary. So if you want to increase voltage, you have to increase the number of turns in secondary. So when a stabilizer increase voltage, it's basically increasing the number of turns in secondary. When it decrease voltage, it is decreasing the number of turns in secondary. Now, after this, we can also calculate relation between current and number of turns. Say, power. Okay, I'm calculating one more time. I'm assuming I'm taking one more approximation. Okay, before this assumption, let's take efficiency. Let's study efficiency of transformer. Here, efficiency means the output power. Efficiency is the ratio of output power over input power. Here, output power means power across the secondary. The power is this, VSIS. Across prime, input is output power means power across secondary. Input power means power across primary. So that's VP, IP. This is the efficiency. See what basically efficiency means. If I say that a transformer is say 60% efficient, see what does it mean practically? This means this is your power supply. This is your power supply. AC power supply. Through this AC power supply, you connected a transformer. It's a transformer. And from this transformer, you connected it is something else, like you connected a device, say you connected an AC. So 60% efficiency, not AC, you connected something else. Say you connected a fridge. This is fridge. So 60% efficiency means if this transformer takes 100 joule from the power supply, then out of that 100 joule, it will transfer only 60 joule to the fridge. The rest of the 40 joule will be wasted in the form of heat. This is the meaning of efficiency. If I say that transformer is 100% efficient, that would mean if it takes 100 joule from the power supply, it is transferring all 100 joule to the fridge. But practically, nothing is 100% efficient. There is always some loss of energy. So this is efficiency of transformer. Now, if I assume, let's take one more assumption. Let's call this as some equation. That says equation number 1. Let's call this as equation number 2. Now, I'm assuming 100% efficiency. Means I'm assuming that there is no loss in energy. It's in practical case. No? Which means eta is equal to 1. In equation 2, I'm substituting eta equal to 1 in equation 2. If I substitute this value of eta here, then you will get eta is VSIS over VPIP. If I multiply it here, then this VPIP is its VSIS. Or you can say that VS by VP is IP by IS. That is the relation between voltage and current. That's it. So this is equation number 3. I can do one more thing. See, you know that Vs by Vp is equal to Ns by Np. So by using 1 and 5, I can connect current with the number of turns. So if I substitute 3, 1, means instead of Vs by Vp in this equation, I am substituting Ip by Is. I would get that Ip by Is is Ns by Np. Let's call this as equation number 4. 4, right? There's one more thing. Just always remember that the ratio of Ns by Np is known as turn ratio. This is what we call turn ratio. That is turn ratio basically. The number of turns in secondary and number of turns in primary. They are known as turn ratio. This is also known as transformation ratio. This is also known as transformation ratio. Okay. Now, your transformer can either increase the voltage or it can decrease the voltage. So if your transformer is increasing the voltage, we call this as step up transformer. So what happens in a step up transformer so that it can increase voltage? In a step up transformer, this turn ratio is greater than 1. If turn ratio is greater than 1, that means Ns is greater than Nv. You know that Vs by Vp is Ns by Np. If Ns by Np is greater than 1, that means Vs by Vp is greater than 1. which means Vs is greater than Vp. Voltage at secondary is greater than voltage at primary. This is known as step-up transform. So step-up transform means it increase voltage. But you can see while increasing voltage, it will decrease current. If I take equation of current, see, this is equation of current. Ip by Is is Vs by Vp. Ip by Is is Vs, not Vs, it's Ns by Np. If I say that Ns by Np is greater than 1, that means Ip by Is is greater than 1. If it is greater than 1, that means Ip is greater than Is, or I can say that Is is less than Ip. So see, it increase voltage, but it decrease current. So step-up transformer convert low voltage at high current. So initially voltage is low and current is high. To high voltage, it increase voltage, but at low current, it decrease current. So this is how a step-up transformer works. It decrease current to conserve energy, because energy is voltage into current. A transformer is not a source of energy. It cannot increase energy. It's not that. Okay, Jameer. The next is step down. So step down transformer decrease voltage. So in a step down transformer, Ns by Np is not greater than 1, it's less than 1. Means the number of turns in secondary is less than number of turns in primary. So Vs by Vp is not greater than 1, it's actually less than 1. So it's not greater than 1, it's less than 1. Less than, greater than. So it's less than 1. Vs is less than Vp. Ip by Is is less than 1. It's less than 1. Is is greater than Ip. So it's decreasing voltage but increasing current. So you can write that step-up transformer converts high voltage at low current to low voltage at high current. It converts high voltage at low current to low voltage at high current. This is step-down transformer. Okay, so the next is next question. So the answer of part 1 is it's 10,000. The answer of part 2 is 5 ampere. The answer of part 3 is 22,000 volt. Fourth is 0.05 volt. Part fifth is 1100 watt.